8th grade Open Up Resources Illustrative Mathematics. Unit 7, Lesson 1. Problem number 1. Write each expression using an exponent. A. 1 times 7 times 7 times 7 times 7 times 7. Written as an exponent, that would be 7 to the 5th power. B. 1 times 4/5 5 different times. As an exponent, that's equivalent to 4/5 to the power of 5, or 4/5 to the 5th power. C. 1 times 9.3 8 different times. Expressed as an exponent, that would be 9.3 to the power of 8. D. The number of coins Jada will have on the 8th day if Jada starts with 1 coin and the number of coins doubles every day. She has 2 coins on the first day of doubling. Doubling 2 coins for 8 days would be 2 to the power of 8. Problem number 2. Evaluate each expression. A. 2 to the 5th power. That's the same as 2 times 2 times 2 times 2 times 2, and that equals 32. B. 3 to the power of 3. That would be expressed as 3 times 3 times 3, which is equal to 27. C. 4 to the 3rd power. That's 4 times 4 times 4, which is equivalent to 64. D. 6 to the 2nd power. That could be expressed as 6 times 6, which is 36. E. 1/2 to the power of 4. That can be expressed as 1/2 times 1/2 times 1/2 times 1/2, which is equal to 1/16. F. 1/3 to the power of 2. That would be 1/3 times 1/3, which is equal to 1/9. Problem number 3. Claire made $160 babysitting last summer. She put the money in a savings account that pays 3% interest per year. If Claire doesn't touch the money in her account, she can find the amount she'll have the next year by multiplying her current amount by 1.03. A. How much money will Claire have in her account after 1 year and after 2 years? To find the amount she'd have after 1 year, multiply 160 by 1.03. After 1 year, Claire would have $164.80 in her account. To find out how much Claire would have in her account after 2 years, you need to multiply $164.80 by 1.03. After 2 years, Claire would have $169.74 in her account. B. How much money will Claire have in her account after 5 years? Explain your reasoning. Let's build a table. The column on the left will be the number of years. The column in the middle will multiply the previous balance by 1.03, and the column on the right will be the balance. After the first year, the balance was $164.80. After the second year, the balance was $169.74. To make the balance more accurate, I'm going to multiply the entire decimal number by 1.03. So 169.744 times 1.03 equals 174.83632. which is approximately $174.84. To find the balance in year 4, we need to multiply 174.83632 times 1.03, and that equals 180.0852, which is approximately $180.09. Now finally, to find the balance after 5 years, we need to multiply 180.0852 times 1.03, which equals 185.487756, which is approximately $185.49. This can also be done by multiplying 160 times 1.03 to the power of the number of years. So for example, if we put an x to represent the number of years, it would be 160 times 1.03 to the power of x. Simply substitute the x with the number of years. We'll use this strategy for C. Write an expression for the amount of money Claire would have after 30 years if she never withdraws any money from the account. Substitute the exponent x with 30. So the expression would read 160 times 1.03 to the power of 30. You can also see that using an x as a multiplication symbol can be quite confusing, and some people might mistake it as a variable. By removing the x, it still reads 160 times 1.03 to the power of 30. To save time, you can see that I'm using a calculator to multiply 160 times 1.03 to the power of 30. And the answer is 388.361,99539, which is equivalent to 388.36. or $388.36. Number 4, the equation y equals 5,280x gives the number of feet y in x miles. What does the number 5,280 represent in this relationship? There are 5,280 feet in 1 mile. Problem number 5. The points 2 and 4 and points 6 and 7 lie on a line. What is the slope of the line? We can use this formula to find the slope of these two sets of points. M, the slope, will always be equal to the difference of the y values divided by the difference of the x values. So we can write this as m equals y2 minus y1 over x2 minus x1. Now let's rewrite this as m equals y2, and y2 is 7 minus y1. y1 is 4 over x2. x2 is 6 minus x1, and x1 is 2. Since 7 minus 4 is 3 and 6 minus 2 is 4, m equals 3 over 4. So the slope is 3 over 4. Problem number 6 from 8th grade, Unit 2, Lesson 6. The diagram shows a pair of similar figures, one contained in the other. Name a point and a scale factor for a dilation that moves the larger figure to the smaller one. In the lower left-hand corner of the graph, you'll see I've identified center point A. And here I've identified the larger figure by outlining it in blue. And here you can see I've outlined the smaller figure. The larger figure has a height of 6 units and a base of 3 units. And the smaller figure has a height of 2 units and a base of 1 unit. The larger shape is 3 times larger than the smaller shape, and the smaller shape is 1/3 the size of the larger shape. The scale factor for a dilation that moves the larger figure to the smaller figure would be a 1/3 scale factor, because the larger figure would have to reduce its size to 1/3 of its original size. You can show your support for my YouTube channel by subscribing and leaving a comment in the comment section below. Thanks for watching, and I'll see you next time. Eighth grade, open up resources, illustrative mathematics. Unit 7, Lesson 2, multiplying powers of 10. Problem number 1. Write each expression with a single exponent. A. 10 to the power of 3 times 10 to the power of 9. Exponent 3 plus exponent 9 equals exponent 12. So the answer would be 10 to the power of 12. B, 10 times 10 to the power of 4. That's the same as 10 times 10 4 more times, for a total of 10 times 10 5 different times. On the first 10, that's really 10 to the power of 1. An exponent of 1 plus an exponent of 4 equals an exponent of 5. So this would be 10 to the power of 5. C, 10 to the power of 10 times 10 to the power of 7. So that's multiplying 10 by itself 10 times and then another 7 times. So an exponent of 10 plus an exponent of 7 equals an exponent of 17. So 10 to the power of 10 times 10 to the power of 7 would equal 10 to the power of 17. D, 10 to the power of 3 times 10 to the power of 3. That's a total of 10 to the power of 6. You're going to multiply 10 times itself 6 times. E, 10 to the power of 5 times 10 to the power of 12. Exponent 5 plus exponent 12 equals exponent 17. So you're going to multiply 10 times itself 17 different times. So 10 to the power of 5 times 10 to the power of 12 equals 10 to the power of 17. F, 10 to the power of 6 times 10 to the power of 6 times 10 to the power of 6. Exponent 6 plus exponent 6 plus exponent 6 equals exponent 18. 10 to the power of 6 times 10 to the power of 6 times 10 to the power of 6 equals 10 to the power of 18. Problem number 2. A large rectangular swimming pool is 1,000 feet long, 100 feet wide, and 10 feet deep. The pool is filled to the top with water. A, what is the area of the surface of the water in the pool? To find the area of a rectangle, you need to multiply the length times the width. So in this case, we'd have to multiply 1,000 feet times 100 feet. And 1,000 times 100 is 100,000 feet. So the area would be two-dimensional, 100,000 feet squared. B, how much water does the pool hold? That's going to be the volume, which is three-dimensional. So we'll need to multiply 1,000 times 100 times 10. And that would be 1,000,000 feet to the third power, or 1,000,000 cubic feet. C, express your answers to the previous two questions as powers of 10. Let's look at A. A was 1,000 times 100 to get 100,000. Well, 1,000 is 10 times 10 times 10, which is 10 to the power of 3, times 100, which is 10 times 10, or 10 to the power of 2. Exponent 3 plus exponent 2 equals exponent 5. So A would be 10 to the power of 5 square feet. Now let's look at B. B is almost exactly the same as A, except for they're also multiplying it by 10. And that's a 10 to the power of 1. Exponent 5 plus exponent 1 equals exponent 6. And it's three-dimensional. So B would be 10 to the power of 6 cubic feet. Problem number 3 from 8th grade, Unit 2, Lesson 7. Here is triangle ABC. Triangle DEF is similar to triangle ABC, and the length of EF is 5 centimeters. What are the lengths of sides DE and DF in centimeters? I've put the similar triangle DEF on the right-hand side, and you can see that side EF is labeled as 5 centimeters. 5 centimeters is half of 10 centimeters, which is the length of the corresponding line BC on triangle ABC. That tells me that all the corresponding sides for triangle DEF will be half the length of their corresponding sides for triangle ABC. Half of 6 centimeters is 3 centimeters, and half of 8 centimeters is 4 centimeters. The length of side DE is 3 centimeters, and the length of side DF is 4 centimeters. Problem number 4 from 8th grade, Unit 3, Lesson 3. Elena and Jada distribute flyers for different advertising companies. Elena gets paid 65 cents for every 10 flyers she distributes, and Jada gets paid 75 cents for every 12 flyers she distributes. Draw graphs on the coordinate plane representing the total amount each of them earned, Y after distributing X flyers. Use the graph to decide who got paid more after distributing 14 flyers. I've labeled the horizontal axis, the x-axis, as number of flyers distributed, and the y-axis, the vertical axis, as the amount earned. Along the horizontal axis, the x-axis, the number of flyers distributed, I counted in increments of 2, from 0 through 20. And along the vertical axis, the y-axis, I counted in increments of 10, from 0 to 100. The information tells us that Elena got paid 65 cents for delivering 10 flyers. So I can put a point at 10, 65. 10 along the x-axis and 65 along the y-axis. Jada got paid 75 cents for delivering 12 flyers. So I can put a point at 12 along the x-axis and 75 along the y-axis. We can figure out how much that is per flyer. Elena got paid 65 cents for delivering 10 flyers. 65 divided by 10 is 6.5. That's 6.5 cents per flyer. 6.5 times 14 equals 91 cents. So Elena gets paid 91 cents for delivering 14 flyers. Jada gets paid 75 cents for delivering 12 flyers. 75 divided by 12 equals 6.25. And 6.25 cents times 14 flyers equals 87.5 cents. Jada gets paid 87.5 cents for delivering 14 flyers. Since 91 cents is greater than 87.5 cents, Elena gets paid more for delivering 14 flyers. You can support my YouTube channel by subscribing, liking this video, and leaving a comment. Thanks for watching. See you next time. Eighth grade, Open Up Resources, Illustrative Mathematics. Unit 7, Lesson 3, Powers of 10. Problem number 1. Write each expression with a single exponent. A. 10 to the 7th power, all squared. That means 10 to the 7th power squared, or 10 to the 7th power times 10 to the 7th power. Exponent 7 plus exponent 7 equals exponent 14. 10 to the 7th power all squared equals 10 to the power of 14. B. 10 to the 9th all cubed. That means 10 to the 9th times 10 to the 9th times 10 to the 9th. Exponent 9 plus exponent 9 plus exponent 9 equals exponent 27. 10 to the 9th power all cubed equals 10 to the power of 27. C. 10 to the 6th power all cubed. That means 10 to the 6th power times 10 to the 6th power times 10 to the 6th power. Exponent 6 plus exponent 6 plus exponent 6 equals exponent 18. So 10 to the 6th power all cubed equals 10 to the power of 18. D. 10 to the 2nd power all cubed. That means 10 squared times 10 squared times 10 squared. Exponent 2 plus exponent 2 plus exponent 2 equals exponent 6. 10 to the power of 2 all cubed equals 10 to the power of 6. E. 10 to the 3rd power all squared. That means 10 to the 3rd power times 10 to the 3rd power. Exponent 3 plus exponent 3 equals exponent 6. So 10 to the 3rd power all squared equals 10 to the 6th power. F. 10 to the 5th power all to the 7th power. For this one, I'd like to show you a different way. You can multiply that exponent 5 times the exponent that's on the outside of the parentheses. And 5 times 7 is 35. So f would be 10 to the 35th power. Let's go back and use this strategy on the previous problems. A, 10 to the 7th power, all to the 2nd power. So exponent 7 on the inside times exponent 2 on the outside. And the answer would be 10 to the power of 14. B, 10 to the 9th power, all to the 3rd power. Exponent 9 times exponent 3 equals exponent 27, 10 to the power of 27. C, 10 to the power of 6, all to the power of 3. Exponent 6 times exponent 3 on the outside equals 10 to the power of 18. D, 10 squared, all to the 3rd power. Exponent 2 times exponent 3 equals exponent 6, 10 to the power of 6. E, 10 to the 3rd power, all squared. So exponent 3 times exponent 2 equals exponent 6, 10 to the power of 6. And of course f, 10 to the power of 5, all to the 7th power. Exponent 5 times the exponent 7 on the outside of the parentheses, and the answer is 10 to the power of 35. Problem number 2. You have 1 million number cubes, each measuring 1 inch on a side. A, if you stack the cubes on top of one another to make an enormous tower, how high would they reach? Explain your reasoning. If the side of each cube measured 1 inch and you stacked 1 million cubes on top of one another, the height of the tower would be 1 million inches. B, if you arrange the cubes on the floor to make a square, would the square fit in your classroom? What would its dimensions be? Explain your reasoning. The side lengths of the square would be 1,000 inches long to form a square that has an area of 1 million inches squared. Since 1 foot is 12 inches, we can divide 1,000 inches by 12, and that equals 83.3 feet. A square with side lengths of 83.3 feet long would make an awfully large square, probably too big for a classroom. C, if you layered the cubes to make one big cube, what would be the dimensions of the big cube? Explain your reasoning. The side lengths would be 100 inches because 100 times 100 times 100 equals 1 million inches cubed, and we have 1 million cubes with side lengths of 1 inch. Problem number 3 from 8th grade, Unit 7, Lesson 1. An amoeba divides to form 2 amoebas after 1 hour. 1 hour later, each of the 2 amoebas divides to form 2 more. Every hour, each amoeba divides to form 2 more. If we sketch this out, we'll have a better visual. Hour 0, we start with 1 amoeba. After 1 hour, there's 2 amoeba. After 2 hours, there's 4 amoeba. And after 3 hours, there's 8 amoeba. We answered A because after 1 hour, there were 2 amoeba. And we answered B. After 2 hours, there were 4 amoeba. C. Write an expression for the number of amoeba after 6 hours. Let's go back to our illustration and you'll notice a pattern. At hour 0, when there's 1 amoeba, the expression is 2 to the power of 0. After hour 1, when there's 2 amoeba, the expression is 2 to the power of 1. After 2 hours, the expression is 2 to the power of 2. After 3 hours, the expression is 2 to the power of 3. I can continue to follow this pattern, and after 6 hours, the expression would be 2 to the power of 6. And 2 to the power of 6 is 64. So the number of amoeba after 6 hours would be 64. D. Write an expression for the number of amoeba after 24 hours. I'm going to continue with this pattern, and the expression will be 2 to the power of 24. And 2 to the power of 24 is 16,777,216. E. Why might exponential notation be preferable to answer these questions? Exponential notation is much simpler to write than very large numbers or very small numbers. And what I mean by very large or small numbers is numbers that have many place values. Problem number 4 from 8th grade, Unit 4, Lesson 15. Elena noticed that 9 years ago, her cousin Katie was twice as old as Elena was then. Then Elena said, "In 4 years, I'll be as old as Katie is now." If Elena is currently E years old and Katie is K years old, which system of equations matches the story? Since Elena noticed this 9 years ago, that would have been Elena's age minus 9 and Katie's age minus 9. And so 9 years ago, Katie was twice as old as Elena. So I'm going to go with D. K minus 9 equals 2 times E minus 9. And E plus 4 equals K, which is Elena's age plus 4 equals Katie's age. I think that 9 years ago, Elena must have been 4 years old and Katie must have been 8 years old. Now, Elena is 13 years old and Katie is 17 years old. Before we get started, show your support by hitting that like button. 8th grade, Unit 7, Lesson 4, Dividing Powers of 10. Problem number 1. Evaluate. A. 10 to the power of 0. Well, we know that any number to the power of 0 always equals 1. I made a tutorial explaining this, so if you want to know why any number to the power of 0 always equals 1, click the link in the description box or click the link in the above right-hand corner. B. 10 to the power of 3 over 10 to the power of 3. So any number divided by itself is always equal to 1. 10 to the third power divided by 10 to the third power is like 1 divided by 1 because they cancel each other out, and you can replace each of them with a 1 when they cancel each other out. C. 10 squared plus 10 to the power of 1 plus 10 to the power of 0. That's the same as 10 times 10 plus 10 plus 1, which equals 111. Problem number 2. Write each expression as a single power of 10. A. 10 to the power of 3 times 10 to the power of 4 over 10 to the power of 5. That's the same as 10 times 10 times 10 times 10 times 10 times 10 times 10 over 10 times 10 times 10 times 10 times 10. Each time we have 10 divided by 10, they cancel each other out. It turns out that all 5 on the bottom are canceled out, and 5 of them on top are canceled out, just leaving on top 10 times 10, with an imaginary 1 on the bottom. So it's 10 times 10 over 1, or 10 to the power of 2 divided by 1, which equals 10 to the power of 2. B. 10 to the power of 4 times 10 to the power of 12 over 10 to the power of 7. 10 to the power of 4 is the same as 10 to the power of 4 over 1. We can rewrite this as a fraction, which is a division problem, as 10 times 10 times 10 times 10 times 10 times itself 12 more times, for a total of 10 times itself 16 times, over 10 to the power of 7, which is 10 times itself 7 times. And as it turns out, we have more on top, so all the ones on the bottom are canceled out, and 7 of them on top are canceled out. Since 16 minus 7 is 9, the answer is 10 to the power of 9 over 1, which is the same as 10 to the power of 9. C. 10 to the power of 5 divided by 10 to the power of 3, all to the power of 4. This means that we'll have 10 to the power of 5 times itself 4 different times over 10 to the power of 3 times itself 4 different times. Again, we're going to cancel them out, so we can cancel out 10 to the power of 3 on the bottom, turn that into an imaginary 1, and take away 3 from 10 to the power of 5, and that becomes 10 to the power of 2. So now it reads 10 to the power of 2 times 10 to the power of 2 times 10 to the power of 2 times 10 to the power of 2. That means that we're multiplying 10 times itself 8 different times. So the expression can be written as 10 to the power of 8. For letter D, we have 10 times itself a total of 15 times on top, and 10 times itself a total of 10 times on the bottom. So all 10 of them on the bottom are canceled out, and we can substitute that with an imaginary 1, and we take 10 away from 15 on top, so we have 10 times itself 5 times. 10 to the power of 5 over an imaginary 1, and that equals 10 to the power of 5. For letter E, we have 10 to the power of 5 to the second power divided by 10 to the second power to the third power. That means 10 to the power of 5 times 10 to the power of 5 over 10 to the power of 2 times 10 to the power of 2 times 10 to the power of 2 on the bottom. Now we can start canceling out. Cancel out 10 to the second power on the bottom and change the top to 10 to the third power. Cancel out another 10 to the second power on the bottom and change the next 10 to the fifth power to 10 to the third power. Cancel out the last of the 10 to the second power from the bottom and cancel out 10 to the second power from the top. 10 to the sixth power minus 10 to the second power is 10 to the fourth power. Problem number 3. The sun is roughly 10 to the second power times as wide as the Earth. The star KW Sagittarius is roughly 10 to the power of 5 times as wide as the Earth. About how many times as wide as the sun is KW Sagittarius? Explain how you know. KG Sagittarius' width is 10 to the power of 5 times larger than the width of the Earth, and the Sun is 10 to the power of 2 times larger than the width of the Earth. So 10 to the power of 5 divided by 10 to the power of 2 equals 10 to the power of 3, because the 10 to the power of 2 at the bottom cancels out, and you have to cancel out 10 to the power of 2 from 10 to the power of 5, leaving 10 to the power of 3. And 10 to the power of 3 is 1,000. KG Sagittarius is 1,000 times wider than the Sun. Problem number 4 from 8th grade Unit 5 Lesson 3. Bananas cost $1.50 per pound and guavas cost $3 per pound. Kieran spends $12 on fruit for a breakfast his family is hosting. Let B be the number of pounds of bananas Kieran buys and G be the number of pounds of guavas he buys. A. Write an equation relating the two variables. Since the bananas cost $1.50 per pound, we can use 1.5b, and since guavas cost $3 a pound, we can use 3g. Since Kieran spends $12, the equation would read 1.5b plus 3g equals 12. B. Rearrange the equation so b is the independent variable. We need to get the g by itself, so let's subtract 1.5b from both sides. Now that 1.5b is canceled out on the left side of the equal sign, the equation reads 3g equals 12 minus 1.5b. Divide both sides by 3 so that we have just 1g. 3g divided by 3 equals 1g, or g, and 12 minus 1.5b divided by 3 equals 4 minus 0.5b. The equation now reads g equals 4 minus 0.5b. C. Rearrange the equation so g is the independent variable. Now we need to get the b by itself. Let's subtract 3g from both sides, and the equation reads 1.5b equals 12 minus 3g. Divide both sides by 1.5 to get 1b, and you have b equals 8 minus 2g. Problem number 5 from 8th grade Unit 3 Lesson 1. Lynn's mom bikes at a constant speed of 12 miles per hour. Lynn walks at a constant speed of 1/3 of the speed her mom bikes. Sketch a graph of both of these relationships. The horizontal axis, or the x-axis, is time in hours, and the vertical axis, or the y-axis, is distance in miles. I noticed that this graph doesn't go all the way up to 12 miles for the 12 miles per hour. I can use 6 miles per half hour. Starting at the origin, I can draw a line through 6 miles per half hour to represent Lynn's mom's constant bike speed. Since 1/3 of 12 is 4, I can draw the line that represents Lynn's constant walking speed, starting at the origin through 4 miles per hour. You can show your support for my YouTube channel by liking this video, leaving a comment, and subscribing to my channel. Thanks, I appreciate it. See you next time. Eighth grade Open Up Resources Illustrative Mathematics. Unit 7, Lesson 5. Negative exponents with powers of 10. Problem number 1. Write with a single exponent. A. 1/10 times 1/10 times 1/10. Written with a single exponent, that would be equivalent to 10 to the power of -3. B. This time, 1/10 is multiplied by itself 7 different times. So this is going to be equivalent to 10 to the power of -7. C. Inside the parentheses, we have 1/10 times 1/10 times 1/10 times 1/10. That's 4 different times. Outside the parentheses, we have to the power of 2. So that means we need 2 sets of 1/10 times itself 4 different times. That's a total of 1/10 times itself 8 times, because 8 is 2 groups of 4. 1/10 to the power of 8. Written as a single exponent, that would be 10 to the power of -8. D. Inside the parentheses, we have 1/10 times itself 3 different times, And outside the parentheses, we have to the power of 3. That means we need 3 groups of 1/10 times itself 3 times. That's a total of 9 times. Written as a single exponent, that would be 10 to the power of negative 9. E. 10 times 10 times 10 inside the parentheses, and outside the parentheses is the power of negative 2. That's equivalent to 1 over 10 times 10 times 10 to the power of 2, which is 2 groups of 1 over 10 times 10. So that would be 1 over 10 times 10 times 10 times 1 over 10 times 10 times 10, which is 1 over 10 to the power of 6. Written with a single exponent, that would be 10 to the power of negative 6. Once again, 1 over 10 to the power of 6 is equivalent to 10 to the power of negative 6. Problem number 2. Write each expression as a single power of 10. A. 10 to the power of negative 3 times 10 to the power of negative 2. We can rewrite that as 1/10 times 1/10 times 1/10. That represents 10 to the power of negative 3 times 10 to the power of negative 2. 1/10 times 1/10. Altogether, we have a total of 1/10 times itself 5 different times, which is equal to 1 over 10 to the power of 5. Written as a single power of 10, this would be 10 to the power of negative 5. A quicker way to do it would be to add their exponents. Negative 3 plus negative 2 equals negative 5. So 10 to the power of negative 3 times 10 to the power of negative 2 equals 10 to the power of negative 5. B. 10 to the power of 4 times 10 to the power of negative 1. Remember, the quicker way would be to add their exponents. The power of 4 plus the power of negative 1. 4 plus negative 1, or 4 minus 1, equals 3. So 10 to the power of 4 times 10 to the power of negative 1 equals 10 to the power of 3. C. 10 to the power of 5 over 10 to the power of 7 equals, on the top of the fraction, 10 times itself 5 different times, and on the bottom of the fraction, 10 times itself 7 different times. 10 divided by 10 equals 1, and 10 divided by 10 equals 1. 10 divided by 10 equals 1, 10 divided by 10 equals 1, and 10 divided by 10 equals 1. What's left is 1 times 1 times 1 times 1 times 1 on the top, which is 1, and 1 times 1 times 1 times 1 times 1, which is 1, times 10 times 10 on the bottom. That's the same as 1 over 10 times 10, or 1 over 10 to the power of 2. To write this as a single power of 10, would be 10 to the power of negative 2. D. Inside the parentheses, 10 to the power of negative 4, and outside the parentheses, the power of 5. That means 5 groups of 10 to the power of negative 4, or 10 to the power of negative 4 times itself 5 different times. We can add the exponents. Negative 4 plus negative 4 plus negative 4 plus negative 4 plus negative 4, and that's a negative 20. A shortcut would be to multiply the power of negative 4 times the power of 5. Negative 4 times positive 5 equals negative 20. This expression, written as a single power of 10, would be 10 to the power of negative 20. E. 10 to the power of negative 3 times 10 to the power of positive 2. Remember, since they have a common base number, in this case, their bases are 10, we can add their exponents. Negative 3 plus a positive 2, and that equals negative 1. To rewrite this expression using a single power of 10, we would write 10 to the power of negative 1. F. 10 to the power of negative 9 over 10 to the power of 5. That's equivalent to 10 to the power of negative 9 times 10 to the power of negative 5. Now they have the same base number, and we can add their exponents. Negative 9 plus a negative 5. That's a total of negative 14. So when we rewrite this expression, we can write 10 to the power of negative 14. Problem number 3. Select all of the following that are equivalent to 1 over 10,000. Let's look at A. Inside the parentheses, you have 10,000. Outside the parentheses, you have a negative 1. 10,000 to the power of negative 1 is equivalent to 1 over 10,000. so I would select A. Let's look at B, negative 10,000. No, because negative 10,000 has the value of negative 10,000, which is different than 1 over 10,000. C, inside the parentheses, we have 100, and outside the parentheses, we have the power of negative 2. And that's equivalent to 1 over 100 to the power of positive 2, which is the same as 1 over 100 times 100. And since 100 times 100 is 10,000, then I would select C. D, inside the parentheses, we have 10, and the exponent on the outside of the parentheses is negative 4. 10 to the power of negative 4. We could make that a positive exponent by placing it on the bottom. Now it reads 1 over 10 to the power of positive 4. Since 10 to the power of positive 4 is 10,000, then I would select D, because 10 to the power of negative 4 is equivalent to 1 over 10,000. And finally, E. Inside the parentheses, we have negative 10, and outside the parentheses, we have to the power of positive 2. That represents negative 10 times negative 10, or negative 10 squared. Since a negative times a negative is a positive, and 10 times 10 is 100, the value for E is 100, so I would not select E. Problem number 4 from 8th grade, Unit 3, Lesson 2. Match each equation to the situation it describes. Explain what the constant of proportionality means in each equation. I can match equation A, y equals 3x, with situation 2. I am making a water and salt mixture that has 2 cups of salt for every 6 cups of water. We have cups of water and cups of salt. There are 6 cups of water and 2 cups of salt. 2 divided by 2 equals 1. That makes 1 cup of salt. And 6 divided by 2 equals 3. That makes 3 cups of water. For this situation, I have 3 cups of water for each cup of salt. So for this equation, y could represent the amount of water, and x represents the number of cups of salt. When x is 2, 3 times 2 equals 6, or the number of cups of water. When x is 1, the number of cups of salt, 1 times 3 equals 3, the number of cups of water. Equation B could match situation 4. For every 48 cookies I bake, my students get 24. There are the cookies I bake and the cookies my students get. When I bake 48 cookies, my students get 24 cookies. 48 divided by 48 equals 1. 24 divided by 48 equals 1/2. When the number of cookies I bake is just 1, my students get 1/2. This means for every cookie I bake, my students get half. If I baked 48 cookies, my students would get half of 48, which is 24 cookies. Equation B matches with situation 4. Equation C is a match with situation 1. A dump truck is hauling loads of dirt to a construction site. After 20 loads, there are 70 square feet of dirt. There are the number of loads and square feet of dirt. When the number of loads is 20, the square feet of dirt is 70. Divide both of these by 20. 20 divided by 20 is 1, or 1 load, and 70 divided by 20 is 3.5, or 3.5 square feet of dirt. So for every 1 load, there's 3.5 square feet of dirt. The dump truck hauls 3.5 square feet of dirt in each load. So equation C matches with situation 1. Let's look at equation D. Equation D matches with situation 3. A store has a 4 for $10 sale on hats. We have the number of hats and the amount of dollars. When there are 4 hats, the price in dollars is $10. Divide both sides by 4. 4 divided by 4 is 1, or 1 hat, and $10 divided by 4 is 2.5, or $2.50. That means that hats cost $2.50 each. Again, equation D matches with situation 1. Problem number 5 from 8th grade, Unit 2, Lesson 8. A. Explain why triangle ABC is similar to triangle EDC. Both triangles contain a right angle, and angles ACB and ECD are vertical angles. The triangles are similar because two pairs of corresponding angles are congruent. B. Find the missing side lengths. We can use these two corresponding side lengths to help us find the missing side lengths. 39 over 26. That's the same as 39 divided by 26, which is 1.5 or 1.5. That means that the scale factor is 1.5 or 1.5. Length CD is 1.5 times longer than length BC, and length DE is 1.5 times longer than length AB. 1.5 times 10 is 15, so side DE measures 15 units, and 36 divided by 1.5 is 24, so side BC measures 24 units. Be sure to support my YouTube channel by liking this video, leaving a comment, and subscribing to my channel. Thanks for watching, and I'll see you next time. Eighth grade Open Up Resources Illustrative Mathematics, Unit 7, Lesson 6. What about other bases? Problem number 1. Priya says, I can figure out 5 to the power of 0 by looking at other powers of 5. 5 to the power of 3 is 125. 5 to the power of 2 is 25. Then 5 to the power of 1 is 5. A. What pattern do you notice? I notice that when a power of 5 drops by 1, the value is divided by 5. For example, 125 divided by 5 is 25, and 25 divided by 5 is 5. B. If this pattern continues, what should be the value of 5 to the power of 0? Explain how you know. Let's review the pattern. 125 divided by 5 is 25. 25 divided by 5 is 5. And 5 divided by 5 is 1. So 5 to the power of 0 would be 1. C. If this pattern continues, what would be the value of 5 to the power of negative 1? Explain how you know. 5 to the value of negative 1 equals 1/5 because the value of 5 to the power of 0, which is 1, divided by 5 is 1 divided by 5, or 1 over 5, which is 1/5. Problem number 2. Select all the expressions that are equivalent to 4 to the power of negative 3. 4 to the power of negative 3 can be written as 1 over 4 to the power of positive 3. And that can be expressed as 1/4 times 1/4 times 1/4. And that's equal to 1 over 64. Let's take a look at expression A. Expression A is negative 12, and since negative 12 is not equal to 1 over 64, I will not select expression A. Let's look at expression B, 2 to the power of negative 6. We can rewrite this with a positive exponent. That would be 1 over 2 to the power of 6, or 2 times 2 times 2 times 2 times 2 times 2, which equals 64. So the value for expression B is equal to 1 over 64, so I would choose expression B. Let's look at expression C, 1 over 4 to the power of 3. That's the same as 1 over 4 times 4 times 4, which is equal to 1 over 64, so I would choose expression C. Expression D is 1/4 times 1/4 times 1/4, and we know that that equals 1 over 64, so we can choose that one. Expression E is 12, and 12 certainly is not the same as 1 over 64, so we can't choose that one. Expression F is a negative times a negative times a negative, which is a negative, and 4 times 4 times 4 is 64, and we know that negative 64 is not the same as positive 1 over 64, so we can't choose F. And finally, expression G, 8 to the power of negative 1 over 2 to the power of 2. 8 to the power of negative 1 can be rewritten as 1 over 8. And 2 to the power of 2 is 4. So that's equivalent to 1 over 8 times 4. And since 8 times 4 is 32, this value is 1 over 32, which is not equivalent to 1 over 64. So we can't choose G either. Problem number 3. Write each expression using a single exponent. A, 5 to the power of 3 over 5 to the power of 6. 5 to the power of 3 is 5 times 5 times 5, and 5 to the power of 6 is 5 times itself 6 times. 5 divided by 5, that's worth 1. And 5 divided by 5 is also worth 1, and 5 divided by 5 is worth 1. So on top we have 1 times 1 times 1, or 1, and on the bottom we have 1 times 1 times 1 times 5 times 5 times 5. That's equivalent to 1 over 5 to the power of 3. Using a single exponent, we can write this as 5 to the power of negative 3. Expression B, 14 to the power of 3 on the inside of the parentheses and to the power of 6 on the outside of the parentheses. We can multiply these exponents and we have 14 to the power of 18. Expression C, 8 to the power of 3 times 8 to the power of 6. Since they have the same base, you can add the exponents. The power of 3 plus the power of 6 is the power of 9. 8 to the power of 3 times 8 to the power of 6 is 8 to the power of 9. Expression D, 16 to the power of 6 over 16 to the power of 3. That's the same as 16 to the power of 6 divided by 16 to the power of 3. We need to subtract the exponents. Since 6 minus 3 is 3, we have 16 to the power of 3. E, inside the parentheses we have 21 to the power of 3, and on the outside of the parentheses we have the power of negative 6. We can multiply these exponents. 3 times negative 6 is negative 18, so we have 21 to the power of negative 18. Problem number 4 from 8th grade Unit 5, Lesson 6. Andre sets up a rain gauge to measure rainfall in his backyard. On Tuesday, it rains off and on all day. A, which of the two graphs could represent Andre's story? Explain your reasoning. Well, there's a couple clues. He starts at 10 a.m. with an empty gauge when it starts to rain. Here you can see on graph A, it starts at 10 a.m. with 0 rain in his gauge. And graph B doesn't start at 10 a.m. So for that reason alone, I'm going with graph A. B, label the axes of the correct graph with appropriate units. It says here that 2 hours later he checks the gauge and the gauge has 2 centimeters of water in it. That means that the units would be hours and centimeters. The horizontal units across the bottom are time of day in hours, and the vertical units are centimeters, representing the height of the water in the rain gauge. It also mentions that it starts raining even harder at 4 p.m. The rain stops, so Andre checks the rain gauge and finds it has 10 centimeters of water in it. C, use the graph to determine how much total rain fell on Tuesday. If I look at the graph along with what I just read, I can see that on Tuesday at 4 o'clock, there was a total of 10 centimeters of water in the gauge. So I'd say the total is 10 centimeters. It also mentions that Andre was checking it and he accidentally knocked the rain gauge over and spilled most of the water, leaving only 3 centimeters of water in the gauge. This is represented in the graph. I've drawn an arrow to the graph that marks this event. It also mentions that he checks for the last time at 5 p.m. and there is no change. That means that it hasn't rained since the last time he checked it. Be sure to support my YouTube channel by liking this video, leaving a comment, and subscribing to my channel. Thanks for watching, and I'll see you next time. 8th grade Open Up Resources Illustrative Mathematics. Unit 7, Lesson 7. Practice with rational bases. Problem number 1. Write with a single exponent. A. 7 to the power of 6 over 7 to the power of 2. That's 7 times itself 6 times divided by 7 times itself twice. We could cancel out 7 times 7 on top and 7 times 7 on the bottom. 7 times 7 divided by 7 times 7 is 1, so we can replace that with a 1, and we're left with 7 to the power of 4 over 1, which is 7 to the power of 4. B. 11 to the power of 4, all to the power of 5. That means we have 11 to the power of 4 times itself 5 times. Since there's an exponent on the outside of the parentheses, we're going to multiply these exponents. 4 times 5 equals 20. So our answer would be 11 to the power of 20. C. 4 to the power of 2 times 4 to the power of 6. 4 to the power of 2 would be 4 times 4, and 4 to the power of 6 would be 4 times itself 6 different times, for a total of 4 times itself 8 times. So our answer would be 4 to the power of 8. We just added the exponents. 2 plus 6 is 8. D. 6 times 6 to the power of 8. Well, 6 would be 6, and then 6 to the power of 8 is 6 times itself 8 times. So that would be a total of 6 times itself 9 different times, or 6 to the power of 9. Since 6 is the same as 6 to the power of 1, we really just added the exponents. The invisible exponent 1 plus 8 equals 9. E. 12 to the power of 2, all to the power of 7. That would be 12 to the power of 2 times itself 7 different times. Since we have the exponent on the outside of the parentheses, we're going to multiply these exponents. 2 times 7 equals 14. So that would be a total of 12 to the power of 14. F. 3 to the power of 10 over 3. That's the same as 3 times itself 10 different times on top, divided by 3. We'll cancel out the 3 on the bottom and one of the 3's on the top, and we'll replace those with 1. So we're left with 3 to the power of 9 over 1, which is equal to 3 to the power of 9. If you think about it, we really subtracted the exponents. 10 minus the invisible 1 exponent. 10 minus 1 is 9. G. 0.173 to the power of 9 times 0.173 to the power of 2. That's 0.173 times itself 9 different times, and then multiplying itself times 0.173 2 more times, for a total of 11 times. So the answer would be 0.173 to the power of 11. You can see here we just added the exponents. 9 plus 2 is 11. H. 0.87 to the power of 5 divided by 0.87 to the power of 3. Cancel out 0.87 times itself 3 times from the bottom, and we canceled that out 3 times from the top, leaving just 0.87 times itself 2 times. So our answer would be 0.87 to the power of 2. If you notice, we subtracted the exponents. 5 minus 3 is 2. I. 5 halves to the power of 8 divided by 5 halves to the power of 6. Cancel out all 6 from the bottom and cancel out 6 of the 8 on the top. That leaves 5 halves times 5 halves. Since that's over 1, it's the same as 5 halves to the power of 2 divided by 1, which is 5 halves to the power of 2. Problem number 2. Noah says that 2 to the power of 4 times 3 to the power of 2 equals 6 to the power of 6. Tyler says that 2 to the power of 4 times 4 to the power of 2 equals 16 to the power of 2. A. Do you agree with Noah? Explain or show your reasoning. 2 to the power of 4 means 2 times itself 4 times. times 3 to the power of 2. That means multiply times 3 times itself twice. So you would end up with 2 times 2 times 2 times 2 times 3 times 3. And that does not equal 6 times 6 times 6 times 6 times 6 times 6. So I disagree with Noah. B. Do you agree with Tyler? Explain or show your reasoning. 2 to the fourth power is 2 times 2 times 2 times 2, and 4 to the second power is 4 times 4. So the question is, does 2 times 2 times 2 times 2 times 4 times 4 equal 16 times 16? 16 times 16 is 256, and 2 to the power of 4 times 4 to the power of 2 also equals 256, because 2 times 2 is 4, again, 2 times 2 is 4, and 4 times 4 is 16, and 4 times 4 is 16, and 16 times 16 equals 256. So I do agree with Tyler. Be sure to support my YouTube channel by liking this video, leaving a comment, and subscribing to my channel. Thanks for watching, and I'll see you next time. Eighth grade Open Up Resources, Illustrative Mathematics, Unit 7, Lesson 8, numbers 1 through 4. 2 to the power of 8 times 2 to the power of 9. The bases are the same, but the exponents are different. We can look at 2 to the power of 8 as 2 times itself 8 different times. And we can look at 2 to the power of 9 as 2 times itself 9 different times. 2 to the power of 8 times 2 to the power of 9 equals 2 to the power of 17. Since the bases are the same, we can keep the base as 2 and add the exponents. 8 plus 9 is 17, so 2 to the power of 8 times 2 to the power of 9 equals 2 to the power of 17. Now let's try one that has the exponents the same, but the bases are different. 8 to the power of 2 times 9 to the power of 2. Since the exponents are the same, we can put the exponent on the outside of the parentheses and put the bases on the inside. 8 times 9 equals 72. So 8 to the second power times 9 to the second power equals 72 to the second power. So if the bases are different but the exponents are the same, we can multiply the bases and keep the exponent the same. 8 squared times 9 squared equals 72 squared. Number 2, multiplying exponents. Find x, y, and z if 3 times 5 all to the fourth power times 2 times 3 all to the fifth power times 2 times 5 all to the seventh power equals 2 to the power of x times 3 to the power of y times 5 to the power of z. Take a moment to look at it and think of a strategy. Press pause if you'd like more time to think about it. One helpful thing that I noticed is that the base numbers are only 2, 3, and 5. Let's start with a 2 and see how many times we have the base number 2 and the number of their exponents. We can see that we have the base number 2 twice. The first base number 2 has the exponent 5, and the second base number 2 has the exponent 7. And 5 plus 7 is 12. Or 2 to the fifth power times 2 to the seventh power equals 2 to the 12th power. Now let's move on to the next base, 3. So we'll look to see how many different times we see a 3 as the base in the parentheses. I see two base numbers, 3. The first base number 3 has a 4 as its exponent, and the second base number 3 has a 5 as its exponent. 4 plus 5 equals 9. Or 3 to the power of 4 times 3 to the power of 5 equals 3 to the power of 9. So finally, let's look for the base number 5. Why don't you try this one on your own? Look to see how many times you see the base number 5, what their exponents are, and add the exponents together. Press pause if you'd like more time to find the answer on your own. I can see that there's 2 base number 5s. The first base number 5 has an exponent of 4, and the second base number 5 has an exponent of 7. And 4 plus 7 equals 11. Or 5 to the power of 4 times 5 to the power of 7 equals 5 to the power of 11. X equals 12, Y equals 9, and Z equals 11. Let's solve this a different way. First, let's use the distributive property and bring the exponents to all the base numbers inside the parentheses. Then we can combine the like terms. 2 to the power of 5 times 2 to the power of 7 equals 2 to the power of 12. 3 to the 4th power times 3 to the 5th power is 3 to the 9th power. 5 to the 4th power times 5 to the 7th power is 5 to the 11th power. In this case, the value for x is 12, the value for y is 9, and the value for z is 11. Number 3, multiplying exponents. This example shows the multiplication of exponents. You'll notice an exponent on the outside of the parentheses. This exponent goes with each of the bases on the inside of the parentheses. For example, 3 to the power of 3 times 5 to the power of 3. And you noticed once I moved that exponent to the bases on the inside of the parentheses, I was able to remove the parentheses. And since this expression is only dealing with multiplication, we can rearrange the order of the terms. This 5 is actually 5 to the power of 1. When I combine 5 to the power of 1 with 5 to the power of 3, it becomes 5 to the power of 4. I combined those two terms for a reason. And that reason is, now I can multiply 5 to the 4th power times 2 to the 4th power. Again, I can rearrange the terms to make this easier for me. I know that 2 to the 4th power times 5 to the 4th power is 10 to the 4th power. To illustrate why, I can take their common factor, the power of 4, and put it outside the parentheses. And 2 times 5 all to the power of 4 is equivalent to 10 to the power of 4. Now the expression looks a little bit different. 3 to the power of 3 times 10 to the power of 4. Let's take a quick look to see how we got to this point. 3 times 3 times 3 equals 27, and 10 times 10 times 10 times 10 equals 10,000, and 27 times 10,000 equals 270,000. Let's try another expression. This example involves multiplying exponents and dividing by a term with an exponent. First, I'll use the distributive property to distribute the exponents from outside the parentheses to the terms that are inside the parentheses. And after completing that step, I can remove the parentheses altogether. I'm doing this so I can reorder the terms. Notice that the divisor, or the denominator, is 3 to the power of 2. Now look at the dividend, or the numerator, and you'll also notice a 3 to the power of 2. That's the same as 3 to the power of 2 divided by 3 to the power of 2, which is 1. Essentially, they've canceled each other out. I notice terms with the base of 5 and 2. I like that because 5 times 2 equals 10. 5 to the power of 2 times 2 to the power of 2 is the same as 5 times 2 all to the power of 2. Which of the remaining pair of terms would you match with this 5 to the power of 2 to make it easier for you. I would choose the term that has 2 as its base because 5 times 2 equals 10, and that makes it easier for me. But I am going to add just a bit of a challenge. I'm going to take that exponent that's attached to the 5 inside the parentheses, and I'm going to move it outside of the parentheses. Look at the 2 remaining terms at the top of the screen, 2 to the 3rd power and 3 to the 2nd power. It looks like 3 to the 2nd power is the only term that I can choose to use with the 5 inside the set of the parentheses because the exponent on the outside of the parentheses is a 2. But since I'd like to use the term with a base of 2, watch what I do. Let me show you that again. I'm taking the 2 to the power of 3 and I'm changing it to 2 to the power of 2 times 2 to the power of 1. I leave 2 to the power of 1 up there with 3 to the power of 2. So now inside the parentheses I have 5 times 2 all to the power of 2. Let's look again. 2 to the power of 3 becomes 2 to the power of 2 times 2 to the power of 1. And I take the 2 to the power of 2 and I insert it into the parentheses. Now we have 5 times 2 all to the power of 2. 5 times 2 is 10, and 10 to the 2nd power is 100. 100 times 100 is 10,000. 3 to the 2nd power, or 3 times 3, is 9. 2 times 9 is 18. I'll let you take it from here, but essentially, it's 10,000 times 18 times 1 divided by 1. Hopefully your answer is 180,000. Number 4. The cost of cheese at 3 stores is a function of the weight of the cheese. The cheese is not prepackaged, so a customer can buy any amount of cheese. Right away, I notice some differences. Store A sells the cheese for A dollars per pound, but Store B sells the same cheese for B dollars per pound, and a customer has a coupon for $5 off the total price at that store. So that's a coupon that takes $5 off of the price. Store C is an online store selling the same cheese at C dollar per pound, but with a $10 delivery fee. So they're tacking on a $10 fee for every order. When I look at this graph, right away I see this line that starts at 0 pounds of cheese at $10. So that makes me think that this might be Store C, the store that charges a delivery fee of $10. At the bottom of the graph, you'll find the horizontal axis. And the horizontal axis represents the weight of the cheese in pounds. And along the left side of the graph, you'll find the vertical axis, which represents the cost in dollars. At the bottom left corner of the graph, you'll find the origin. That represents 0 pounds of cheese and 0 cost in dollars. Directly above the origin, I labeled a point that represents $10 for 0 pounds of cheese. And you can see the cost of cheese increasing as the number of pounds increase. Look at the horizontal axis, the weight of cheese. Between 4 and 6, you'll find 5 pounds. 5 pounds of cheese at this particular store costs exactly between $20 and $30, which would be $25. So in this case, or at this store, 5 pounds of cheese costs $25. I could write an equation or a function that would help me calculate how much it would cost to buy a particular amount of cheese at this store. 5 times what number plus 10 equals 25? Since we're talking about line J, I'll replace the question mark with a J. This is a 2-step equation. I'd like to find the value for J. And I'll do that by getting the j by itself on the left-hand side of the equal sign. First, I'll start by getting rid of the positive 10, and I'll subtract 10 from both sides. 10 minus 10 and 25 minus 10. 10 minus 10 cancels each other out, so we have 5j equals 25 minus 10, and 25 minus 10 is 15. Since there's only one step left, we can call this a one-step equation. 5j equals 15. I still need to get the j alone, so 5 divided by 5 and 15 divided by 5. 5j divided by 5 is 1j, and 1j is the same as j, and 15 divided by 5 is 3. J equals 3. J represents store C. Store C sells cheese for $3 per pound. Now let's go back to the graph and look at line K. This is interesting because 1 pound of cheese costs $0 and 2 pounds of cheese costs $5. That makes me think that if you used a coupon for $5 off of 1 pound, that you could get 1 pound of cheese for $0. Line K must represent store B, the store that had a $5 coupon. 1 pound would be free, 2 pounds would be $5, 3 pounds would be $10, 4 pounds would be $15. Let's use that as our equation or our function. 4 times what number minus $5 equals $15. Since this equation or function represents line K, I replace the question mark with K. Now it reads 4K minus 5 equals 15. This is a two-step equation, and in order to get the K by itself, first I need to add 5 to both sides. I'm adding 5 to both sides to cancel out that negative 5. So when I add 5 to negative 5, it cancels it out. 4K minus 5 plus 5 equals 15 plus 5. 4K minus 5 plus 5 is 4K, and 15 plus 5 is 20. So now it reads 4K equals 20. Now it's a one-step equation. All we have to do now is get the K by itself. I need to divide both sides by 4. 4K divided by 4 and 20 divided by 4. 4K divided by 4 equals 1K, or just K. And 20 divided by 4 equals 5. So now it reads K equals 5. Line K represents a store that would sell cheese for $5 a pound. Line K represents store B. Store B sells cheese for $5 per pound. That leaves store A, and store A sells cheese for $8 per pound. Let's go back to the graph and take a look at the remaining line so that we can identify what exactly is $8 per pound. Look at line L and the point where it intersects 5 pounds of cheese and $20. We can write a one-step equation to represent this. 5 times what number equals $20? Since we're dealing with line L, I'll replace the question mark with the letter L. Now the function or the equation reads 5L equals 20. With one step, we should be able to solve for L. Divide both sides by 5. 5L divided by 5 is 1L, which is the same as L. And 20 divided by 5 is 4. L equals 4. Line L represents store A. Store A sells cheese for $4 per pound. Match stores A, B, and C with graphs J, K, and L. Store A matches with line L. Store B matches with line K. Store C matches with line J. How much does each store charge for the cheese per pound? Store A charges $4 per pound, Store B charges $5 per pound, and Store C charges $3 per pound. How many pounds of cheese does the coupon for Store B pay for? For store B, a $5 coupon would pay for 1 pound of cheese because at store B, a pound of cheese costs $5, the same amount as the coupon. Which store has the lowest price for a half pound of cheese? Look at line K. With a $5 coupon, 1 pound of cheese would cost $0. 1 pound for store B is $0, so a half a pound would be $0. Store B has the lowest price for a half a pound of cheese. If a customer wants to buy 5 pounds of cheese for a party, which store has the lowest price? Look at lines J and K. Do you see where they intersect? They intersect exactly at the point of 5 pounds of cheese and $20. And above that, you can see line J represents 5 pounds of cheese at $25. Lines L and K represents stores A and B. They both have the lowest price for 5 pounds of cheese. How many pounds of cheese would a customer need to order to make store C a good option? Line J represents store C. Follow line J left to right. It intersects line L, and then it finally intersects line K at 10 pounds of cheese. What this means, if the customer were to buy more than 10 pounds of cheese, line L or store C would be the best option. Ordering more than 10 pounds makes store C the best option. You can check out more illustrative mathematics tutorials. Read the video description for more info. If it's worth watching, it's worth subscribing. So please take a moment to become a subscriber. I really appreciate it. Thanks for watching. Eighth grade Illustrative Mathematics, Unit 7, Lesson 9, Describing Large and Small Numbers Using Powers of 10. Problem number 1. Match each number to its name. A. You have a 1 followed by 6 zeros. And after the 6 zeros would be where the decimal point belongs. So in this case, the number is 1 million. A matches with 5, 1 million. B, 0.01. That's 1 0 to the left of the decimal point and 1 0 to the right of the decimal point, followed by a 1. That would be 1/100th. B matches with 1, 1/100th. C, 1 followed by 9 zeros. And to the right of the 9 zeros is the decimal point, so that would be 1 billion. C matches with 6, 1 billion. D, 0 point, and then there's 5 zeros followed by a 1. That would be 1 millionth. D matches with 3, 1 millionth. E, 0.001. So you have the decimal point and then 2 zeros to the right followed by a 1. That would be 1,000th. E matches with 2, 1,000th. F, 1 followed by 4 zeros to the right, and then to the right of the last 0 there's a decimal point. That would be 10,000. F matches with 4, 10,000. Problem number 2. Write each expression as a multiple of a power of 10. A. You have a 4, a 2, and a 3, followed by 2 zeros. Those 2 zeros mean that the value of this number is 100 times larger than 423. So we can write 423 times 10 to the second power, because 10 to the second power means 10 times 10, which is 100. And 423 times 100 would be 42,300. B. 2 followed by 3 zeros to the right. Those 3 zeros tell me that the value of this number is 1,000 times bigger than 2. So we can write 2 times 10 to the power of 3. 10 to the power of 3 is 10 times 10 times 10, which would be 1,000. And 2 times 1,000 is 2,000. C. We have a 9 and a 2 followed by 5 zeros to the right. Those 5 zeros tell me that the value of this number is 100,000 times larger than 92. So we can write 92 times 10 to the power of 5. D. 4,000. That's 4 followed by 3 zeros. Those 3 zeros tell me that the value of this number is 1,000 times greater than 4. So we can write 4 times 10 to the power of 3. E. 80 million. That's an 80 followed by 6 zeros, or an 8 followed by 7 zeros. The 7 zeros tell me that the value of this number is 10 million times greater than 8. So we can write 8 times 10 to the 7th power. F. 32 billion. That's a 3 and a 2 followed by 9 zeros. The 9 zeros tell me that the value of this number is 1 billion times greater than 32. So we can write 32 times 10 to the power of 9. This lesson is preparing you to learn how to write in scientific notation. Let's do that now. When you write an expression in scientific notation, you're going to have the decimal put directly after the first digit. So in this case, instead of being 423, it'll be 4.23. And since we moved the decimal 2 places to the left, we need to increase the exponent by 2. So now it becomes 10 to the power of 4 instead of 10 to the power of 2. Both of these examples are expressions that are written as a multiple of a power of 10. So you can use one or both of these answers. B. 2 times 10 to the third is already written in scientific notation. C. 92 times 10 to the power of 5. In scientific notation, we could write that as 9.2 times 10 to the power of 6. Since we moved the decimal point 1 place to the left, we have to remember to increase the exponent by 1. So it goes from 10 to the 5th power to 10 to the 6th power. D. 4 times 10 to the power of 3. That's already written in scientific notation. E. 8 times 10 to the power of 7. That's also already written as scientific notation. F. 32 times 10 to the power of 9. Written in scientific notation, we'll move the decimal point 1 place to the left, so now it reads 3.2 times 10 to the power of 10. Problem number 3. Each statement contains a quantity. Rewrite each quantity using a power of 10. Let me give you an example. 14 thousandths. That's written as 0.014. We can rewrite that using a power of 10 by moving the decimal point all the way right, so it reads 14. And to express it using a power of 10, we can write 14 times 10 to the power of -3. And if you wanted to write it using scientific notation, we would put the decimal point between the 1 and the 4 and write it as 1.4 times 10 to the power of -2. Let's try A. There are about 37 trillion cells in an average human body. The quantity that we need to rewrite using a power of 10 is 37 trillion. We can rewrite that as 37 times 10 to the power of 12, or we can rewrite that using scientific notation and write 3.7 times 10 to the power of 13. B. The Milky Way contains about 300 billion stars. We need to rewrite 300 billion. We can write that as 3 times 10 to the power of 9, and that's already written in scientific notation. C. A sharp knife is 23 millionths of a meter thick at its tip. We need to rewrite 23 millionths. We can rewrite that as 23 times 10 to the power of -6, Or we can rewrite it using scientific notation, and that would be 2.3 times 10 to the power of negative 5. D. The wall of a certain cell in a plant is 4 nanometers thick. A nanometer is 1/1000th of a meter. We can write that as 4 times 10 to the power of negative 9, and that's also written in scientific notation. Problem number 4, from 8th grade, Unit 5, Lesson 10. A fully inflated basketball has a radius of 12 centimeters. Your basketball is only inflated halfway. How many more cubic centimeters of air does your ball need to fully inflate? Express your answer in terms of pi. Then estimate how many cubic centimeters this is by using 3.14 to approximate pi. The volume of a sphere is given by the formula V equals 4/3 pi r cubed, where r is the radius of the sphere. Since the radius of the basketball is 12 centimeters, we can plug in 12 in place of the r. Since they want me to use 3.14 for pi, I'm going to plug in 3.14 in place of the pi symbol. Now I have all the information I need to find the volume of the fully inflated basketball. Next, I need to find the information to help me find the volume of my basketball that is halfway inflated. I plugged in a 6 for the radius because 6 is half of 12, and it says that my basketball is halfway inflated. And I plugged in 3.14 to approximate pi. To find out how many more cubic centimeters my ball needs to be fully inflated, I'm going to subtract the volume of the halfway inflated basketball from the volume of the fully inflated basketball. I'm going to rewrite the multiplication in these equations so that pi, or 3.14, is at the end. Let's start with a fully inflated basketball. 4/3 times 12 to the third power. Here's a reminder. 4/3, that's the same as 4 divided by 3. So you could do 4 divided by 3 times 12 times 12 times 12, which is 2,304. Next, we would multiply that by 3.14. Now let's work on the halfway inflated basketball. 4/3 times 6 cubed. That's 4/3 times 6 times 6 times 6. That would give us 288. Then we'd multiply that by 3.14. The volume needed will equal the difference between 2,304 and 288 multiplied by 3.14. Or in this case, approximately 2016 times 3.14. In terms of pi, I can write it like this. Now let's find out approximately how many cubic centimeters of air we need to fill the basketball. 2016 times 3.14 is approximately 6,330. So the total volume of air that you would need to continue to fill the basketball would be approximately 6,330 centimeters cubed. Problem number 5, from 8th grade, Unit 4, Lesson 5. Solve each of these equations. Explain or show your reasoning. 2 times 3 is 6, and 2 times negative 2c is negative 4c. Now we have 6 minus 4c equals 30. And to get the term with a c in it to be alone, we need to subtract 6 from both sides of the equal sign. Now to make the term have one positive c, we need to divide negative 4c by negative 4. And we need to divide both sides of the equal sign by negative 4. Since a negative divided by a negative is a positive, this leaves us with 1c, or c. And 24 divided by a negative 4 leaves us with negative 6. So for this first equation, c equals negative 6. For the next one, let's get the term on the left that has the x in it by itself. We can do that by adding 2 to both sides of the equal sign. Now, let's make sure that we have the terms with the x in it on the left side of the equal sign, and we'll leave the 9 on the right side of the equal sign. We can do this by adding 6x to both sides of the equal sign. Next, to get the x to be 1x, we can divide 9x by 9. But we have to remember, whatever we do to one side of the equal sign, we have to do to the other side of the equal sign. For this equation, x equals 1. 5 times b is 5b, and 5 times negative 2 is negative 10. So the equation now reads 31 equals 5b minus 10. Next, I want to get the 5b by itself, so I have to get rid of the negative 10. I can do that by adding 10, but remember, whatever you do to one side, you do to the other side. Now the equation is 41 equals 5b. We want to turn 5b into 1b, and we do that by dividing it by 5, but we have to divide both sides by 5. And since 5 doesn't go into 41 evenly, we can leave it as an improper fraction. b equals 41 fifths. Problem number 6, from 8th grade, Unit 3, Lesson 10. Graph the line going through negative 6, 1 with a slope of negative 2 over 3 and write its equation. Negative 6 is the first number in the set of coordinates, so it moves along the x-axis, and the negative means it moves to the left. We start at the origin where the x-axis and the y-axis intersect, and we move 6 places to the left. The second value they gave us in the coordinates is a 1. That moves along the y-axis. A positive 1 means we move up and put our point. The information tells us that the slope is negative 2 over 3. The slope is rise over run. So the negative 2 is the rise and the 3 is the run. Or the rise could be 2 and the run could be negative 3. We can use this to plot new points. Start at our original point, and for the rise we'll go down 2 because it says negative 2. And for the run we'll go to the right 3 because it's a positive 3. And here we can put our next point. To make our next point, let's start at the first point, and this time let's go up 2. The rise will be a positive 2, and the run is a negative 3. That means we move 3 units to the left. And that's where we can put our third point. We have enough points to draw a line, but I'm going to make one more point. Let's start with a point on the bottom right and go down 2 for the negative 2 rise and to the right 3 for the positive 3 run. Now we can put our fourth point and draw a line. If this was helpful, click that like button and make sure you're subscribed to my channel. I appreciate it. That's it for now, and I'll see you next time. 8th grade Illustrative Math, Unit 7, Lesson 10, representing large numbers on the number line. Problem number 1. Find 3 different ways to write the number 437,000 using powers of 10. Let's start with 437,000 with a decimal point at the end. And let's get rid of the comma since we're going to be moving that decimal point to the left towards the 4. If we move the decimal point to the left one place, it makes it 10 times smaller. So now it's 43,070 times 10 to the power of 1. Move it one more time and you have 4,370 times 10 to the power of 2. Move it a third time and you have 437 times 10 to the power of 3. Move the decimal to the left a fourth time and you have 43.7 times 10 to the power of 4. Move the decimal a fifth time and you have 4.37 times 10 to the power of 5, which is written in scientific notation. These are the 3 different ways that I would write the number 437,000 using powers of 10. However, you could use any of the 5 expressions that I showed you. Problem number 2. For each pair of numbers below, circle the number that is greater. Estimate how many times greater. Fortunately, the first pair of numbers are both being multiplied by the same power of 10. And I know that 17 is about 4 1/4 times greater than 4, so this number is also about 4 1/4 times greater than this number. What are these numbers? Let's put commas in. 1,700,000,000 is also about 4 1/4 times greater than 400 million. The next pair of numbers are also being multiplied by the same power of 10. And since 7.839 is almost 8, it's safe to say that 7.839 is almost 4 times greater than 2. The last pair of numbers are being multiplied by a different power of 10. 42 times 10 to the power of 7. We'll just put 7 zeros to the right of 42. And 8.5 times 10 to the power of 8, we'll move the decimal point 8 places to the right. So counting the 5, that would be 1, and then 7 zeros for a total of 8. Let's put the commas in. Since 850 million is more than 2 times greater than 420 million, then 8.5 times 10 to the power of 8 is more than 2 times greater than 42 times 10 to the power of 7. Problem number 3. What number is represented by point A? Explain or show how you know. That long line segment on the bottom with point A on it is just a zoomed in version of this small segment on the top line. Here it is zoomed in. Let's start from the beginning to find its location. Here's 1 times 10 to the 11th power, 2 times 10 to the 11th power, 3 times 10 to the 11th power, 4 times 10 to the 11th power, 5 times 10 to the 11th power, 6 times 10 to the 11th power, and then now we've gotten to the zoomed in line. 7 times 10 to the 11th power, 7.1 times 10 to the 11th power, 7.2 times 10 to the 11th power, 7.3 times 10 to the 11th power, and here's point A, 7.4 times 10 to the 11th power. That's your answer. Let's keep going. After 7.9 times 10 to the 11th power, we have 8 times 10 to the 11th power. Then 9 times 10 to the 11th power. And since 10 times 10 to the 11th power is 10 to the 12th power, this represents 10 to the 12th power. Problem number 4 from 8th grade Unit 6, Lesson 7. Here's a scatter plot that shows the number of points and assists by a set of hockey players. Select all the following that describe the association in the scatter plot. There is a linear association because all the data on the scatter plot resembles a line or somewhat resembles a line, which means that I can't select the nonlinear association. Since the data that's forming this line is moving upward, that means it's a positive association. Since it's a positive association and moving upward, that means that it's not a negative association moving downward. So I cannot select negative association. I also cannot select E, no association, because there is an association. There's a linear association and a positive association. If there were no association, the scatter plot would look like this, with data points spread all across the scatter plot with no pattern at all. Problem number 5, from 8th grade Unit 5, Lesson 5. Here's the graph of days and the predicted number of hours of sunlight, H, on the dth day of the year, A. Is hours of sunlight a function of days of the year? Explain how you know. H is a function of D. For each value of D, there is only one value of H. B. For what days of the year is the number of hours of sunlight increasing? For what days of the year is the number of hours of sunlight decreasing? From day 0 to day 180, the hours of sunlight are increasing. And from day 180 to day 365, the hours of sunlight are decreasing. C. Which day of the year has the greatest number of hours of sunlight? The highest peak of this graph is day 180. So day 180 has the greatest amount of sunlight. If this tutorial helped you, please hit the like button and make sure you're subscribed. That's it for now. Thanks for watching, and I'll see you next time. 8th grade Illustrative Mathematics, Unit 7, Lesson 11, representing small numbers on the number line. Problem number 1. Select all the expressions that are equal to 4 times 10 to the power of negative 3. To write this as a decimal, start with a 4 and move the decimal to the left 3 places. And the decimal value is 4 thousandths, which means it's not equal to F, which is 4 ten-thousandths. It is equal to E, 4 thousandths, and not equal to D, which would be equal to 4 ten-thousandths. It is equal to C, which would be 4 thousandths. It is not equal to b because that wouldn't be a decimal. That's just negative 4,000. And finally, it is equal to a, which would be 4 thousandths, because 1/10 times 1/10 is 1/100th, and 1/100th times 1/10 is 1,000ths. And 4 times 1,000ths is 4 thousandths. Problem number 2. Write each expression as a multiple of a power of 10. A, 4 hundredths. So we start with the 4 in the hundredths place. And to write this expression as a multiple of power of 10, we can start with a 4, multiply it by 10 to a negative power because we're representing a decimal. Since the decimal point is 2 place values to the left of the 4, the exponent will be a negative 2. B, 72 thousandths. We can write that as 7.2 times 10 to a negative power because we're representing a decimal. Since the decimal is 2 places to the left of the 7, the exponent will be a negative 2. C. We can rewrite this one as 3.25 times 10 to a negative exponent because we're representing a decimal. And since the decimal is 5 places to the left of the 3, the exponent will be a negative 5. D. 3 thousandths. That's a decimal written with a 3 in the thousandths place. We can express this as a multiple of a power of 10 by multiplying 3 times 10 to a negative power because we're representing a decimal. And since the decimal is 3 places to the left of the 3, the exponent is a negative 3. E, 23 hundredths. That means that the 3 is in the hundredths place. So we can write this as 0.23. To write this expression as a multiple of a power of 10, we can write 2.3 times 10 to a negative power because 23 hundredths is a decimal. And since the decimal is only 1 place to the left of the 2, then the exponent is a negative 1. We can rewrite the expression 729 thousandths as a multiple of a power of 10 by writing 7.29 times 10 to a negative power because it's representing a decimal, and the exponent is a negative 1 because the decimal is only 1 place to the left of the 7. We can write the expression 41 millionths as a multiple of a power of 10 by writing 4.1 times 10 to a negative power because it represents a decimal. And since the decimal is 5 place values to the left of the 4, then the exponent's a negative 5. Problem number 3 from 8th grade, Unit 3, Lesson 9. A family sets out on a road trip to visit their cousins. They travel at a steady rate. The graph shows the distance remaining to their cousin's house for each hour of the trip. A. How fast are they traveling? The horizontal line along the bottom, or the x-axis, represents time in hours, and the vertical line, or the y-axis, represents distance in miles. In glancing at the line, I noticed that between hours 7 and 8, they traveled from 0 miles to 60 miles. That means that they're going 60 miles every 1 hour, or 60 miles an hour. B. Is the slope positive or negative? Explain how you know and why that fits the situation. In looking at the line, I can see the slope. On the left-hand side, up on top, it heads down to the right, and that means a negative slope. And that fits the situation because as time goes by, there are fewer and fewer miles remaining. C. How far is the trip and how long did it take? Explain how you know. We can look at distance in miles, or the y-axis, and see that the length of the trip is 480 miles. We can look at the x-axis, or the time in hours, and see that the trip took 8 hours. Let's double check our work. Remember they said that they were traveling at a constant rate of 60 miles an hour? Well, 480 divided by 8 equals 60 miles an hour. If this video was helpful, please hit the like button and make sure that you're subscribed to my channel. That's it for now. Thanks for watching, and I'll see you next time.